Welcome back. Before we start our deep dive into today's topic, please take a second to hit that like button, subscribe to the channel, and turn on notifications so you never miss a technical breakdown. It really helps the channel grow. Welcome to this deep dive into the Apache Spatial Information System, a powerful yet often overlooked component of the Apache ecosystem that enables spatial data processing and geospatial analysis. In this video, we'll explore its architecture, key features, and how it integrates with modern web applications. Apache SIS is particularly useful for developers working with mapping APIs, GIS pipelines, or web-based geospatial services. It also integrates seamlessly with Apache HTTP Server for serving spatial data. At the heart of Apache SIS are several core concepts: Coordinate Reference Systems, CRS, which define how spatial data relates to real-world locations; Datum Transformations, which allow conversion between different geodetic systems; Metadata Handling, ensuring compliance with geospatial standards; and support for common geospatial data formats like GeoJSON, KML, and GML. Apache SIS is built on a modular architecture that allows developers to use only the components they need. It integrates with Apache HTTP Server for serving spatial data over REST Pitfalls APIs and web services. This makes it compatible with mapping libraries like OpenLayers and Leaflet, enabling rich interactive maps in web applications. One of the key strengths of Apache SIS is its robust support for Coordinate Reference Systems, CRS. It supports standard EPSG codes and allows for custom projections. Whether you're working with 2D or 3D coordinate systems, SIS provides precise geodetic calculations and integrates metadata standards for consistency and interoperability. Datum transformations are critical when working with data from different geographic regions or systems. Apache SIS offers accurate conversion between geodetic systems, supports both global and local datums, integrates with EPSG transformation grids, and ensures high-precision geospatial operations. Apache SIS ensures metadata compliance with international standards like ISO 19115 and ISO 19139. It supports automated metadata generation, validates data against geospatial standards, and integrates with spatial data catalogs for better discoverability and interoperability. Apache SIS supports a wide range of geospatial data formats including GeoJSON, KML, and GML. It integrates seamlessly with mapping libraries like OpenLayers and Leaflet, supports REST Pitfalls APIs, and provides robust tools for spatial data validation and parsing. Apache SIS integrates with Apache HTTP Server to serve spatial data via REST Pitfalls APIs. It enables dynamic map tile generation, acts as a reverse proxy for geospatial services, and supports TLS SSL for secure data delivery. Apache SIS is optimized for handling large spatial datasets. It supports caching and load balancing for improved performance, offers multi-threaded processing capabilities, and integrates with cloud infrastructure for scalable deployments. Security is a critical aspect of any geospatial system. Apache SIS supports TLS SSL encryption, integrates with Apache's authentication and authorization modules, provides fine-grained access control, and works seamlessly with Apache's security frameworks. A common real-world use case for Apache SIS is as a backend for geospatial APIs. It can serve GeoJSON data over REST Pitfalls APIs, perform coordinate transformations on the fly, generate dynamic map tiles, and integrate with web mapping libraries like Leaflet or OpenLayers. Another powerful use case is building a spatial data transformation pipeline. Apache SIS can batch process geospatial files, perform coordinate system conversions, enrich and validate metadata, and output data in multiple formats like GeoJSON, KML, or GML. Apache SIS can also integrate with traditional GIS platforms like QGIS and ArcGIS. It enables data exchange, synchronizes coordinate systems, standardizes metadata, and provides API-based access to spatial data for these platforms. Dynamic map tile generation is another compelling use case. Apache SIS can render map tiles on the fly, supports multiple projections, integrates with web mapping services, and optimizes performance through caching mechanisms. Apache SIS offers several advantages: robust support for coordinate reference systems, high precision in geospatial operations, a modular and extensible architecture, and strong integration with the broader Apache ecosystem. However, Apache SIS also has some drawbacks. It has a steep learning curve for beginners, a smaller community compared to mainstream GIS tools, and requires a solid understanding of geospatial concepts to use effectively. Apache SIS works well with several related technologies. These include Apache HTTP Server for serving data, Geo Tools for Java-based geospatial processing, PostGIS for spatial database extensions, and mapping libraries like OpenLayers and Leaflet for front-end integration. If you're new to Apache SIS, here's a learning roadmap. Start by understanding coordinate systems and projections, then dive into Apache SIS core concepts and APIs. Next, integrate SIS with Apache HTTP Server, build a geospatial web service, and finally optimize performance and handle large datasets. To get started with Apache SIS, you'll need to download and install it, configure environment variables, verify the installation using sample commands, and explore the built-in tools and utilities it provides. Working with coordinate systems in Apache SIS involves defining CRS using EPSG codes, performing coordinate transformations, validating coordinate inputs, and exporting the transformed data in your desired format. Building a Geospatial API involves setting up Apache HTTP Server, configuring REST-TFL endpoints, integrating with Apache SIS as the backend, and testing with sample requests to ensure everything works as expected. To optimize performance, enable caching mechanisms, use multi-threading for processing, optimize data loading pipelines, and monitor resource usage to identify bottlenecks and improve efficiency. Security best practices include enabling TLS SSL encryption, configuring authentication and authorization, using fine-grained access control, and regularly updating and patching your systems to prevent vulnerabilities. When debugging and troubleshooting, check logs for error messages, validate coordinate system definitions, test transformations with sample data, and use Apache SIS's built-in diagnostic tools to identify and resolve issues. Apache SIS also offers advanced features such as custom projection definitions, integration with cloud services, support for temporal geospatial data, and a plug-in architecture for extending functionality. Apache SIS can be deployed on cloud platforms like AWS, Azure, or GCP. Use containerized deployments for consistency, scale with load balancing, and automate with CI/CD pipelines for efficient management. The Apache SIS community offers several resources: official documentation, community forums and mailing lists, GitHub repositories with examples, and third-party tutorials and guides to help you get started and troubleshoot issues. Looking ahead, Apache SIS is expected to see enhanced cloud integration, improved performance and scalability, support for emerging geospatial standards, and broader community adoption as more developers discover its capabilities. Compared to other GIS tools, Apache SIS excels in web-based geospatial processing. While PostGIS handles database integration, GeoTools offers Java-based processing. QGIS is great for desktop GIS, and Leaflet or OpenLayers are ideal for web mapping. Apache SIS bridges the gap with its web-native architecture. In an urban planning application, Apache SIS can process real-time spatial data, integrate with city planning databases, render dynamic maps for stakeholders, and provide secure access for planning teams to collaborate effectively. In environmental monitoring, Apache SIS can integrate sensor data, perform geospatial analysis of environmental metrics, send real-time alerts, and visualize data for researchers to make informed decisions. In logistics and supply chain management, Apache SIS enables route optimization using spatial data, real-time tracking of shipments, integration with warehouse systems, and dynamic map updates for dispatchers to improve efficiency. For developers, best practices include using version control for configurations, automating testing for transformations, monitoring performance and errors, and documenting APIs and workflows for maintainability and collaboration. Common pitfalls include incorrect CRS definitions, performance bottlenecks with large datasets, security misconfigurations, and inconsistent metadata handling. Avoid these by validating inputs, optimizing pipelines, securing configurations, and standardizing metadata practices. In conclusion, Apache SIS is a powerful tool for geospatial processing, especially in web-based mapping and APIs. It integrates well with the Apache ecosystem, but requires a strong understanding of geospatial concepts to use effectively. For further reading, check out the official Apache SIS website, community forums and mailing lists, GitHub repositories with examples, and third-party tutorials and guides to deepen your understanding. Thanks for watching this deep dive into Apache Spatial Information System. If you found this tutorial helpful, please like, subscribe, and leave a comment below with your use cases or questions. Your feedback helps us create more content like this. Stay tuned for more deep dive tutorials. And that wraps up our explanation. If you found this useful, please hit the like button and share it with a fellow developer. Don't forget to subscribe for more technical tutorials. Thanks for watching, and I'll see you in the next one.